So what are you guys getting for y prime? Yeah, this -1 to the n, you got to be careful. Well, I mean, if you put -2 to the n, you're saying that 2 is being raised to the nth power, which is not true.
So it'd be -1 to the n times 2.
Not just 2. 2n. X to the 2n minus 1. Right, so the beautiful thing about any polynomial, it doesn't matter how you represent the exponent, is bring it down and then take -1 off of it. It doesn't, that's the best rule ever. And what is this?
Is there a chain rule for this, right? 2n? Is 1 by 9?
No, the only function of x in there is x itself. N is a number.
So we're treating n as a constant?
I'm not treating it as a constant, it is a constant.
Oh.
I want you to really understand. N is different for every term in this sum, but for every individual term, n is a constant. So what I'm doing is I'm differentiating an infinite number of terms at once, and they each have a constant based on n. So n is not a function of x at all.
So the derivative of -1 to the n is just 0?
No. The derivative of -1 times x, do you see what I'm saying? It's not just -1 hanging out by itself. It's negative times that thing. So it's still there, just like any constant would be, right? Okay, I like it. All right, now if I try to plug this in to this, let's see what we get. Now here's where things get weird. We got a couple things we've got to figure out. And we might not figure it all out tonight. So 1 plus x squared times this. I'll need you, okay. So that's 1 plus x squared times y prime plus 2x times y. Now, can you guys, now, what can I sort of take care of immediately now? Like what can I do with this stuff here? Distribute, that'd be a good idea. And then we got to worry about like terms. You guys see what I'm saying? You got to worry about like terms somehow. So I get here, I get sum n equals 1. I get 1 times this, so I get this thing. Plus, now when I do x squared in here, what happens? Why can I take x squared in, by the way? Why is that allowed? I can take x squared in, I can take x squared out. Why am I allowed to do that? Because the summations variable is n, right? Or was that even an issue? I don't know. I would hope somebody out there would be like, why didn't you just put x squared in there? Because it's not dependent on n at all. It's a constant related to this, right? Okay. So that means x squared, what do I get then? I get -1 to the n, 2n, x to the 2n plus 1. Plus, go ahead and bring that 2 in there, why not? 2, -1 to the n, x to the 2n plus 1. Yeah, just multiply by 1 more x. No big deal there. Now what's nice about those last two? What's one nice thing and one not so nice thing? What's one nice thing about the last two in terms of like terms? They're like terms, okay. Right? What's not so good is that their indices don't agree. So this is the algebra of summation symbols. I need them to be like terms, and I need the indices to agree before I can slam them together. Now this is where I disagree with the book a bit. The book brings in another summation variable k, and it does all this weird shit. You could do it the book way. I don't like that way myself, personally. So these two have like terms. This one isn't like terms yet, right? These two have like indices, but this one doesn't. So this is the part that you're really, really not used to, right? Your faces are telling me, yeah, I'm not used to this. So, what is one way that I could try to work with this? Let's work with this first. How do I make that become n equal 1? Now there's,
Separate.
how do you mean separated?
Because that includes that. So in n to 0, doesn't that equal n to 1 just with the 0?
Add the first term.
Yeah, so what I can do, I could start to rewrite the summation symbol. I can put a 0 in and write what that is, plus the rest.
Exactly.
That might be sort of sound like what you're kind of going around, but yeah, so you can take this. What's the 0 term look like? If n is 0, what do I get? If n is 0, I get 2 times 1 times x. So I get 2x. And then the rest of it will start at 1, because I just pulled the 0th term off. I like it. So whenever your indices are off, you just pull, whoever's the lowest one, you just pull however many until it becomes the same as everybody else. So now all of our indices are the same. So this one and this one are nice. And just to point out something, these are not really like terms because this doesn't have an n in it. Do you guys see that? But at least their x's pieces are like terms, just in case that becomes necessary. Now, what was the trouble with this guy?
X to the 1 minus 1.
Yeah, his x piece is not like terms with everybody else, right? So what could I do there? Oh, I don't need to do a ratio test or anything.
Like, could you write like x to the 4 and then like break it up so you multiply this way?
So when n is 1, I get, what do I get here? X to the 1. And here I get 2. Now watch, this is, I didn't expect anyone to come up with this, but I didn't know what your background was, so maybe somebody's seen this before. So if I make that, now this is going to look like I'm going backwards for a second, but if I do n equal 0, and then I can do like I did at the end there, right? Now watch, n equals 0, what does that do for me? Well, I don't know, Jeff. This will be -1. Now when n was 1, what did I get here? A 1. So if n is 0, what has to be here so I still get a 1? N plus 1. When n was 1, I got 2 here. So if I just leave it 2n, I'm screwed. If n is 0, I get 0, so I better make it 2n plus 2. So effectively what I'm doing is I'm replacing n with n plus 1 in a way. So here I'm going to get x. Now when n was 1, I got x to the first. If n is 0, I still want to get x to the first, so it better be 2n plus 1. That's probably the freakiest step. But I want you to realize that's part of the ambiguity or the flexibility, whatever the best word is there, with your indices and what's in here. I really want that to make sense. I mean, if I had 1/2, let's see, plus 1/4 plus 1/8 plus ... I could say that would be sum of, what does this look like? 1 over 2 to the n, right? N equal 1 to infinity. But couldn't somebody instead say, no, this is 1 over 2 to the n plus 1. N equals 0 to infinity. Do you guys, I mean, that's inherent in any summation statement, is this little bit of play that you have between these. So that's all I'm doing there. It's actually a very basic idea, but it's something that you don't see done a lot. Because we normally just go, let's do the first thing we think about and not even think about other ways we could do it. So that's all I did there. Was what would this look like if I wanted all the same values, but I wanted to start n at 0. So now I can pull off, what's the first term? If n is 0, because now I've got to make these all the same again. If n is 0, what's the first term I get? It would be negative. Is that cool? If n is 0, it's negative 2x. Negative 2x plus the sum n equals 1 to infinity, negative 1 to the n plus 1, 2n plus 2, x to the 2n plus 1. So now these are all like terms, right? Let me see if you guys can handle me not rewriting everything. So that's this broken up. So look at this, negative 2x plus that 2x, right? Plop, plop. Now watch this is cool. Negative 2n, x to the 2n plus 1, negative 2n, this poor little n. Let me make sure you guys really get this. Where did I leave off my... Well, we're running out of time. I actually got further than I thought I would. Do you see how there's a negative 2n, x to the 2n plus 1? That would cancel with this. Oh, I see. This is exactly what I want. This is always going to be the opposite sign from this, right? You guys see that? So this has got a 2n, x to the 2n plus 1. This has got negative 2n, x to the 2n plus 1. That's going to cancel. And then this is there. So if you distributed this part through, you would get this guy cancels with this guy, that guy cancels with this guy. So everything becomes 0 like it's supposed to be. All right, now obviously, now real quick, just make sure you guys really got that. Whatever sign this is, isn't that always the opposite sign? Because it's n and this is n plus 1. So if n is 2, that's positive, that's negative, right? So it's like, at a time when this is negative 2n, x to the 2n plus 1, this one would be positive 2n, x to the 2n plus 1. They cancel. This piece, at a time when this is negative 2x to the 2n plus 1, that'll be positive 2x to the 2n plus 1. They'll cancel. Yeah?
That piece is 2n plus 3 and the other one is just 2n.
No, it's 2n plus 2, sorry.
How does that cancel with the other? Never mind.
Okay. All right, maybe. Or if you prefer, we could combine these into one single summation statement because they're like terms now with the x's. And that would cancel directly with this, either way. You guys see, so here I'd have 2n of these plus 2 of these is 2n plus 2 of these. Right? And then these are opposite sign from those, so they all cancel. That ends up with 0. I like it.
Once you bring those two together, they're like terms. They're exactly the same.
Exactly. So either you can tear this apart or you can put those together. Either way. Whatever way makes more sense. Both the same. Math doesn't care. I like it. Some of you guys look intrigued. Some of you look like you do this just to torture you. That's part of it. Okay, let me see. Was there one more thing I wanted to say? So, hopefully you understand. That was just a verification problem. So you have to get used to how to kind of manipulate summation series. Now, the nice thing is when we start talking about how to solve these, it's going to be a little more direct as far as this weird shit happens. Because this normally happens more messy with verifying answers. When I go to solve, I assume this is the form, and then I take y prime, and then I plug them in. So it's sort of a standard kind of thing that I'm going to be seeing. You guys see? Whereas the solution could be anything, right? I don't know if you guys really see what I'm saying. So just to help you out a little bit, this kind of business is not going to be as bad when we try to start solving things directly. We're going to assume a solution that looks like this. We're going to take as many derivatives as the DE requires. We're going to plug those in, and then we're going to solve, right? So it's going to be a little more formulaic, whereas if I'm verifying solutions, anything could be happening in here, right? Okay, maybe. Okay. All right, I think that's enough. Yeah, oh yeah. All right.